We're about to jump into one of the biggest leaps forward in computing history. We're talking about a quantum computer that can literally fix its own mistakes while it's running.
So, this is going to sound a little nuts, but what if the most powerful computers ever imagined are actually, for right now, almost completely useless? I know, it's not a riddle. It's the huge paradox that sits right at the heart of quantum computing.
See, on one hand, you've got this incredible, mind-blowing promise. Machines that could design miracle drugs, create materials that sound like science fiction, and maybe even unlock the secrets of the universe itself. But then, there's the cold, hard reality. Today's quantum computers are so unbelievably fragile, so prone to errors, that their calculations just fall apart in less than a blink of an eye. And that right there, that is the single biggest hurdle in this entire field. The race isn't just about building them bigger or faster. It's about getting them to work at all. So it all boils down to this one question. How in the world do you build a reliable machine out of parts that are fundamentally unreliable? Well, the answer is kind of hidden inside this sentence from the breakthrough paper we're looking at today. Now, that probably sounds like complete and utter gobbledygook, right? But I promise you, stick with me. All you need to know for now is that entanglement is this weird, spooky link between particles. By the end of this, you are going to understand exactly what that sentence means and why it changes absolutely everything.
So, to get there, first we really need to wrap our heads around the core problem, this quantum paradox.
Okay, so the basic building block of a quantum computer is something called a physical qubit. This is where all the magic happens. But here's the catch. It is absurdly fragile. The best way to think about it is like a single, really skittish firefly. The tiniest little thing, a stray bit of heat, a tiny magnetic fluctuation, and poof, the light goes out and all your information just vanishes.
So if a single firefly is just too unreliable, what do? Well, you use a whole swarm of them. And that is the beautiful, brilliant idea behind something called a logical qubit. It's not one physical thing. It's a super tough superqubit that's made by encoding one bit of information across many of those fireflies at the same time. It's literally strength in numbers.
And this picture just nails the concept. Think of your important data as a VIP, right? A total rock star. A logical qubit is basically a team of bodyguards. Those are the physical qubits, all surrounding and protecting that VIP. So if one of those bodyguards stumbles, makes an error, the rest of the team instantly closes ranks and protects the VIP. The information survives. It's brilliant.
Okay, so the theory is fantastic. A swarm of bodyguards. Love it. But that brings up a massive engineering problem. How do you actually build and control a computer that can manage all of this in real time? Yeah, this is the billion-dollar question, right? How do you actually choreograph hundreds of these super fragile things so they all act together as one single, flawless unit?
Well, the answer, it turns out, comes from a total shift in how you think about it. You stop thinking of it as a computer chip, and you start thinking of it like a factory. And that's exactly what these researchers at Harvard did. They designed a processor with totally separate zones, each with its own specific job.
And it really works just like a quantum assembly line. First up, you have the storage zone, which is like the warehouse where the logical qubits are all kept safe and sound. Then you have the entangling zone. This is the main factory floor, the assembly line where qubits are brought together to do their calculations. And then, and this part is just so clever, when you need to check a result, individual atoms are physically moved over to a separate readout zone for quality control. Moving them means the act of measuring doesn't disturb anything else happening in the factory. It is an incredibly smart design.
So they built this incredible quantum factory. Now, to really appreciate what they pulled off, we have to talk about the sheer scale of this thing.
The numbers here are just wild. To create just one of their tough, error-resistant logical qubits, the team had to perfectly control up to 280 physical qubits. That's 280 of our little fireflies, all working together in perfect harmony. It's just staggering.
But this all leads us to the single most important question. I mean, all this crazy complexity, the bodyguards, the factory zones, all the extra parts, is it actually better than just using the raw, powerful, but fragile physical qubits on their own?
For decades, the answer to that has been a little disappointing, a lot of not reallys. But now, for the very first time, we have definitive proof of a brand new era. Because for the very first time in the history of this field, the answer to that question is a resounding, definitive yes. This is the moment everything changes.
And the proof comes down to this number, 48. That's the number of robust, error-corrected, logical qubits that the team successfully entangled and ran in a complex algorithm. This is a massive new world record.
And here it is. This is the truly mind-blowing part. They put the two systems into a direct head-to-head competition. And for the first time ever, the logical error-corrected processor didn't just survive. It completely outperformed what was possible with just its physical parts. The whole was finally, actually, greater than the sum of its parts. It didn't just handle errors, it actively beat them.
Okay, so let's just let that sink in for a second. The breakthrough is real. The quantum computer that fixes itself is here. So what on earth does that mean for the future? Well, this isn't just another small step forward. This is the starting gun for an entirely new race. We're talking about the real beginning of error-corrected quantum computing. This gives us a tangible roadmap for building large-scale, truly useful machines. And it kicks the door wide open to solving problems that are currently impossible for even the world's biggest and best supercomputers. So the crucial takeaway here is that the goal is no longer just about building bigger quantum computers, it's about building smarter ones. This research is the blueprint. It's the key that unlocks a realistic path to reliable, powerful processors that can finally start delivering on that incredible quantum promise.
Which leaves all of us with a final and pretty awesome question. Now that we have a machine that can start to compute the incomputable, what impossible problem should we point at it first? If you're as excited as I am about this new era of computing, show some support by hitting that like button, and make sure you subscribe for more explainers that break down our incredible future.